This hearing will come to order. And without objection, the chair is authorized to declare recess at any time. I'd like to welcome our witnesses to the Science, Space, and Technology Committee's hearing entitled Earth's Thermometers, Glacier and Ice Sheet Melt in a Changing Climate. It seems as though we are bombarded on an almost daily basis with news, articles, and reports saying that the world's ice is melting faster than ever. As a matter of fact, I almost invited Mr. Young from Alaska, who moved to Alaska because it was too warm in the United States proper. Since I read about Alaska last week, I thought he might want to hear this. Pictures show ice sheets in Greenland and the Antarctica crashing into the oceans before our eyes. Just last month, a piece of ice the size of the state of Delaware broke off the Antarctica and Greenland and was reported to have experienced the biggest June ice melt event on record, with temperatures 40 degrees above normal. The rate of change in the Arctic and Antarctic has been quickening in recent years, according to the Intergovernmental Panel on Climate Change and numerous other scientific bodies. For example, a study published in Nature in January that was led by an international team of more than 6 dozen researchers tells us that melt rates have more than tripled in western Antarctica in the last 25 years. Mountain glaciers are also experiencing rapid rates of change. Just a few weeks ago, declassified U.S. spy satellite data clearly showed that Himalayan glaciers lost 25% of their ice over the last 40 years. This is equivalent to 8 billion tons of water each year. This puts the hundreds of millions of people in that region who depend on glacier melt as freshwater source at risk. According to the 2014 IPCC assessment report, without significant reductions in global greenhouse gas emissions, mountain glaciers will lose 35 to 85% of their ice by the end of the century under a high emission scenario. New reports indicate that IPCC estimates might even be conservative in that glacier and ice sheet melts rates could even be higher. We need to be listening to Earth's glaciers and ice sheets and what they're telling us about the changing climate. Glacier and ice sheets melt is responsible for 2/3 of the 8 inches of sea level rise that we've seen in the last 200 years from the anthropogenic warming. And that sea level rise is only expected to continue. The Western Antarctic ice sheet, which everyone is watching because it is thought to be the most unstable ice sheet, could add another 11 feet of additional sea level rise if it collapses, which some experts expect could happen at some point. Such an increase would mean many coastal cities would be flooded, and the world as we know it would be different. What's happening in Greenland, Antarctica, and the high mountain regions matter to us all. Glaciers and ice sheets play vital roles in regulating Earth's climate and weather, provide over 2/3 of the Earth's freshwater supply for drinking and agriculture uses, support fisheries and ecosystem health, and run hydropower plants. I'm glad we have the opportunity to hear today from some of the nation's leading glacier and ice sheet experts. And I'd like to welcome Dr. Richard Alley, who last testified before this committee in 2010. I also want to announce that later today, we will be hosting a screening of the award-winning documentary, Chasing Ice, that documents changing ice in the Arctic. It will be followed by a question and answer session with 2 of our witnesses, Dr. Pfeiffer, who was a scientific advisor to the film, and Dr. Moon. The screening is free and open to the public, and I hope all of you will join us. This committee plays an important role in authorizing both climate science and the research needed to better understand glaciers and ice sheets. Since the 1990s, NASA's ice monitoring satellites have led to major discoveries of ice sheet dynamics and melt, while the National Science Foundation has funded major field expeditions in ice sheets. I look forward to today's discussion with our distinguished panel to understand how Congress, and the committee in particular, can address the critical research gaps in this field. Thank you, and I now will offer our ranking member his open statement time.
Thank you, Chairwoman Johnson, for holding this hearing, which is another opportunity to examine the impacts of a changing climate on our country and the world at large. While today's hearings will examine the underlying science of this issue and concerns about climate change, I'd like for us to also focus on the agricultural, economic, and geopolitical consequences we can expect from glacial and sea ice melt, and more importantly, how we can address those. For instance, polar ice sheets cool ocean currents, which affect global weather patterns. As I've mentioned a time or two, weather issues are of paramount importance to farmers and ranchers in Oklahoma and around the world. We do not have a firm grip on how these weather patterns will change due to melting and how we can prepare for these changes. I also want to consider the economic and geopolitical consequences of glacial and sea ice melt. 5 countries, including America and Russia, border the Arctic. Territorial disputes in this region will take on greater importance as resource-rich land and new shipping routes are revealed. There are significant economic implications from the energy rights, mineral deposits, and tourism opportunities. For instance, Russia is claiming that some newly accessible routes should not be considered international waterways, but a part of their sovereign territory. Better research will give us greater insights into how we can expect shipping routes to change so we can prepare to address these issues. As the Science Committee, we have a responsibility to address our national research priorities, and those must be broader than just how the climate's changing. We need to understand the specific effects so we can adopt and continue our economic growth. During our first full hearing of this Congress, members of the committee discussed how we could embrace a broader portfolio of basic research, energy innovation, and competitive technology to make energy production cleaner, more efficient, and less costly. I hope we can spend more time considering research into innovative technologies like nuclear reactors, battery storage, and carbon capture. I'd like to thank our witnesses for being here today, and I look forward to our discussion. And I yield back, Madam Chair.
Thank you very much. I'd like to extend a warm welcome to a guest in the audience, Maria from Chandler, Arizona. Could you stand? We hear you're a rising star. It's a rising senior in high school who is interested in studying engineering in college, and it's great to have the next generation of STEM professionals represented here today. And welcome to our other young people over here, too. Thank you for being here. At this time, I'd like to introduce our witnesses. Our first distinguished witness, Dr. Richard Alley, is the Evan Pugh Professor of Geosciences and Associate of the Earth and Environmental Systems at the Pennsylvania State University. He's spent more than 40 years studying the great ice sheets to help predict future changes in climate and sea levels, and has made 4 trips to the Antarctica, 9 to Greenland, and additional expeditions to Alaska and elsewhere. He has authored or co-authored more than 300 scientific papers. He was involved in IPCC group of contributors that won the 2007 Nobel Peace Prize. He won Pennsylvania State's highest teaching award and has written a book on climate change and ice cores. He holds a PhD in geology from the University of Wisconsin. Our second witness, Dr. Robin Bell, is the PGI Lammert Research Professor at Lammert Doherty Earth Observatory of Columbia University and a member of the faculty at Columbia Earth Institute. She directs programs in ice sheet dynamics, leads efforts to develop innovative technology, and works to improve the scientific culture, especially for women. She has led 10 major expeditions to the polar regions, discovering an active volcano, large deep lakes, and hidden mountain ranges buried by ice. She was instrumental in launching the International Polar Year in 2007 that brought together over 50,000 scientists. Currently, she is the president of the American Geophysics Union, the largest collection of Earth and space scientists in the world, and her PhD is in geophysics from Columbia University. Our third witness is Dr. Twyla Moon, who is a research scientist at the National Snow and Ice Data Center, part of the University of Colorado's Boulder Cooperative Institute for Research in Environmental Sciences. She studies modern changes in glaciers and ice sheets and the connection among ice, climate, ocean, and ecosystems. Her research focuses on the Greenland ice sheet and the Arctic, and uses a variety of tools, including satellite remote sensing, fieldwork, and computer simulations. She also leads efforts to improve science and knowledge co-production between scientists and stakeholders. Dr. Moon received her PhD in Earth and Space Sciences from the University of Washington. Our fourth witness, Dr. Gabriel Walken, is a research scientist and manager of the Climate and Cryosphere Hazards Program in the Alaska Division of Geological and Geophysics Surveys, and a research assistant professor at the University of Arctic Research Center at the University of Alaska, Fairbanks. There, he is a senior scientist in the Climate Adaptation Science Center. He studies snow and glacier change and their connection to climate and natural hazards through observations, remote sensing, and computer modeling. Dr. Walken has a PhD in atmospheric sciences from the University of Alberta. Our final witness, Dr. William Tad Pfeiffer, is a professor of civil, environmental, and architectural engineering and a fellow in the Institute of Arctic and Alpine Research at the University of Colorado Boulder. He has been involved in glaciology research for 40 years, studying the world's mountain glaciers. He has conducted hundreds of field expeditions in the continental USA, Alaska, Canada, Norway, Greenland, Antarctica, and Himalayas, and Africa. He has published over 60 peer-reviewed scientific papers and was a scientific advisor to the Emmy-winning film Chasing Ice. Dr. Pfeiffer earned his PhD in geophysics at the University of Washington. As our witnesses should know, you would each have 5 minutes for your spoken testimony. Your written testimony will be included in the record of the hearing. When all of you have completed your spoken testimony, we will begin a round of questions. Each member will have 5 minutes to question the panel, and so we will begin our witnesses now with Dr. Alley.
Thank you, Madam Chairwoman, Ranking Member Lucas, distinguished members, staff, and citizens for this opportunity to address you. We have high scientific confidence that the world is warming, primarily because we burn fossil fuels and release the CO2. And this is having broad-based impacts. You've asked us to tell you about changes in snow and ice, of which we will get to some of them, but not all. We still have winter, we still have blizzards. Where and when snow and ice care about temperature, we are seeing broad-based shrinkage, and this really is having impacts. Earlier spring snowmelt means that you can lengthen the fire season. It affects ecosystems, it affects tourism. Loss of Arctic sea ice, as Representative Lucas mentioned, has national security implications as well as weather implications. Glacier melt is changing stream flow in some of the most overused and politically sensitive rivers on Earth. I will focus particularly on sea level, which is the biggest global footprint of melting ice. Sea level is rising. Recently, it's been about 1 inch per 8 years. It is rising not because of natural cycles, but because of warming. The ocean expands as it warms. The mountain glaciers are melting, the edges of Greenland are melting and putting extra water into the ocean, and there's faster flow of non-floating ice into the ocean from parts of Greenland and Antarctica. We are committed to some additional sea level rise, just as if you drop an ice cube into your tea, it is committed to melting, but it takes a while to melt. The ice is not caught up with the warming we have already caused. But by the time our students are getting old, the decisions that we humans make now and in the future will grow to be the dominant control on how much sea level rise we experience. This sea level rise is already having implications. You can Google the picture of the octopus in the parking garage in Miami on a high tide, not a storm. But the impacts could become much larger. The general projections are that if we don't change our energy system, we will get something like 3 feet of sea level rise by 2100, above the natural level, the pre-industrial level. And I'd like to speak about the uncertainties in that. Right? So I'd like to do an analogy first. I ride my bicycle to work at Penn State. My wife drives our car, but I drove down here. I saw commuters on the DC area. My impression is that a commuter in DC expects to spend half an hour stuck in traffic. The best thing that can happen to a commuter is no traffic, but they might spend an hour, and they might get run over by a drunk driver and be in the hospital or worse. What they expect, the most likely future, is well on the good end of the possible futures when you get in that car. When we look at sea level rise, it is similar. 3 feet if we don't change our energy system, maybe 2, maybe 4, maybe 5, 10, we're not sure. It could be much worse. And there isn't much better to offset the much worse. There are drunk drivers in the climate system. I'd like to explain one of them. If you ever get the chance to go to Glacier Bay National Park and Preserve in Alaska, it is a gloriously beautiful place. You can cruise 65 miles up the bay and see little glaciers breaking off little icebergs in shallow water, and it's still spectacular. When Vancouver was on his cruise in 1796, there was no Glacier Bay. It was entirely full of ice up to a mile thick. When John Muir went by, less than a century later, the bay was mostly open because icebergs had been breaking off the front of the glacier like dominoes at a rate of up to 7 miles a year, falling over. That process has happened to other glaciers in Alaska. You have world experts on that process here. It has happened in Chile and Svalbard. It's happening in Greenland and the Antarctic Peninsula. It happened to ice sheets in the past. And it's well known that this happens when it gets too warm where ice flows into the ocean. So far, those have been in narrow valleys. They're spectacular locally, but one collapse doesn't raise global sea level a lot. If this starts to happen in parts of Antarctica, rather than a narrow valley, it will open into a broad embayment. If that breaks as rapidly as we have seen elsewhere, in the next century, you might get 10 feet or so of extra sea level rise. It could be faster than that. It is very clear that the uncertainties can be reduced if you fund bright young people to work with the co-panelists up here. That's self-serving, but it's correct. But there may be a little irreducible uncertainty in the same way that you can never predict where every drunk driver might be out on the highway. If we raise temperature, we raise sea level with high confidence, and the uncertainties are it could be a little better, a little worse, or a lot worse. Thank you.
Thank you very much, Dr. Bell.
Thank you very much, Chairwoman Johnson, Ranking Member Lucas, members of the committee. I'm very pleased to be here today. I'm going to take you on a visual tour because the ice sheets are beautiful. I think that's why we all study them. And we want to share a little bit of that beauty with you. So this is a picture of what Antarctica looks like. And just to give you a sense of scale, this is a tiny little iceberg with scientists in front of it. What I'm going to show you today is the evidence for change. I will tell anybody this who stops me anywhere on the street. You stop me on my electric motorcycle, I'm going to tell you this story. There are three signs of really clear signs that the ice sheets are speeding up and changing. One is they're moving faster. In the 1990s, they were moving 1 mile a year. In the 2000s, they're moving 2 miles a year. They've doubled in speed. Ice happens to be like mozzarella cheese on top of your pizza. So when you bite it and stretch it, it gets thinner. So the second measurements we've made is by zapping the ice sheet with a laser, and that's what you see forming, is that yellow on the surface is actually where the elevation, this cheese is getting stretched, the ice sheet's getting stretched. That's more than half a football field, where the ice sheet's getting lower. Second measurement. Our third measurement is one we make, NASA makes with partners, makes from space. Can we turn the video on, the animation on, please? You will see that this is now we're looking at a whole map of Antarctica, and you're going to see a red dot developed. And what that red dot is showing, we're actually losing mass. And remember I showed you it sped up, it lowered. This is a different measurement. This is basically the ice sheet on the bathroom scale. And what you can see is the ice sheet is losing mass predominantly in that place that Richard referred to, the place that's furthest north, exposed to the warming ocean. The ice sheet is losing mass. We could show you the same things for Greenland. Three very clear signals. Kind of the scientific gold standard. We like to make independent measurements. This is the evidence that the ice sheets are changing. What does it mean? When we go to NOAA and we look at NOAA's global collection of tide gauges, so these are really high-tech instruments. They're like pipes stuck in the water, okay? But they measure the tides going up and down and up and down, and they measure storms. The levels go way up, 12 feet in New York during Sandy. But you can see most of those are going up. Sea level almost everywhere on the planet's going up, except where the planet's still recovering from the ice sheet that was here 20,000 years ago, and it's bouncing back up like a mattress. But this predominant signal globally is it's going up. There's even one of those fancy pipes right here in Southeast, and that record goes back to about when my dad was born. And so since my dad was born, right here in Washington, D.C., sea level has gone up a foot. And we're using Beth for scale here. Beth is, for today's purposes, 2 meters or 6 feet, roughly. And you can see, I like to think of it, I put it on my hand on my leg, because then I realize what it really means. That's how far sea level has come up since my dad was born. So what does that mean? We are working on, I'm back to the uncertainty question. Can I tell you how much sea level is going to go up in the next 100 years? We are working on it as hard as we can. This is just a range of forecasts published this year. You can see they are spread. This is, again, Beth for scale, about 6 feet. They range a lot. But when we look, that's what we're working on, is how to be able to tell our communities how much is sea level going to go up in the next 100 years, because that's what we're building infrastructure. The big bridge we just spent $4 billion on close to my house needs to know what we're going to plan for sea level. Are we going to plan for a couple feet or a lot? So when we look at the budget altogether, Antarctica is something in the next 100 years is on the order of maybe over our knees, maybe a little bit more. Greenland's going to be in there too. We're going to have warming oceans, and we're going to have the mountain glaciers. And while I have this as roughly 4 feet, 3 feet, we don't know. This is cutting edge research. And what can we do to improve it? There are, in my mind, there's 3 important things to do. One is get up close and personal. We need to understand better how the ice sheets work so we can improve our models. We used to not be able to have very good models of weather. We do much better now. So one is get up close and personal. Second is we need to invest in the workforce. Right now there are 1,400 scientists in AGU who affiliate with ICE. Do you know there are 140,000 people enrolled in law school every year? We just don't have enough people working on this. We need more scientists, engineers, educators, creative minds like Maria over there. We need to talk her into studying ice somehow. And we also need to look at convergent work. We need to figure out how to pull together the work that we do, which is on the polar caps, to what's happening at the coastlines around the planet, because we kind of need an ice sheet person at every community, because we need to understand what the community needs to respond to. So am I hopeful? Yes, I am hopeful, because we are in a unique place as a species that we know how the ice sheet works. We know how we are understanding how our planet works. And we as scientists, we're all members of the American Geophysical Union, we're actually putting our money where our mouth is. We have a building here in Washington that we just renovated, so it is the first net zero renovation building in Washington, D.C. That means we're taking less energy than we are generating more energy than we're using to run this building. We'd love to have you come to visit. And we're also very happy to look forward, and that this is a time for action among all of us, and we need to bring everybody to the table. Thank you very much.
Thank you very much. Dr. Moon.
Chairwoman Johnson, Ranking Member Lucas, members of the committee, thank you for the opportunity to testify today. Land ice loss has serious consequences within the United States and across the globe, and I'm honored to share my scientific expertise with the committee. Glaciers and ice sheets are Earth's water towers. Only 2.5% of the world's water is fresh water, and most of that fresh water is contained within glaciers and ice sheets, or land ice. As Earth's water towers, glaciers are valuable sources of drinking water, irrigation water, and hydropower. But land ice is now melting at a rapid and accelerating pace, increasing risks for hundreds of millions of people who depend on them for survival and prosperity. And it is raising sea levels across the globe. Today, land ice loss is the biggest contributor to sea level rise. Sea level rise can contaminate drinking water, erode coasts, overwhelm stormwater and wastewater systems, and cause increased or permanent flooding. Over just the last 25 years, our average sea level around the globe has already risen 3 inches. But because sea level rise is not evenly distributed, some areas, like regions of the U.S. Gulf Coast and eastern seaboard, are already dealing with more than double this amount. The impacts we are facing today, however, may pale in comparison to the changes we could experience in the future. If we continue on our current path of high greenhouse gas emissions, it's reasonable to expect 2.5 feet or more of sea level rise in the next 80 years. In regions of the Gulf Coast and the eastern seaboard, that number will be significantly higher. The Greenland ice sheet, which is more than 2 miles thick in its center and covers an area the size of Texas, California, Arizona, and Nevada combined, is an important player in sea level rise. Since the early 2000s, ice loss from Greenland has increased rapidly, and Greenland is now a primary player in land ice contribution to sea level rise. The cause of ice loss is clear. Greenland and glaciers around the world are melting and more rapidly spilling their ice into the sea as a direct result of warming air and warming ocean water due to man-made greenhouse gas emissions. During the last 2 decades, the science community has made substantial strides in understanding Greenland ice sheet behavior and projecting future ice loss. But for any given future greenhouse gas emissions pathway, there is still a large range in projections for how much ice Greenland will lose. Narrowing the range of future possibilities and our projections of them is possible. The United States can lead by supporting targeted research on the physical processes that control ice sheet behavior, by developing systems to collect long-term observations, and by fostering iterative research that connects observations and computer models. Science will also advance more quickly and better serve the public good if strong connections are fostered among scientific disciplines and between scientists and stakeholders. You can ensure this happens by increasing coordinated opportunities for interagency funding and actively funding activities that bring together scientists and decision makers. Finally, I want to emphasize a critical difference in the roles of science and policy in addressing land ice loss and its impacts. Increasing scientific knowledge is essential to more accurately project what the future is likely to bring, given that we are on a particular emissions pathway. But policy has the power to determine which emissions pathway we take. Embarking on a lower emission strategy will make a fundamental difference in how much and how quickly land ice disappears. U.S. leadership on mitigating greenhouse gas emissions within our lifetimes will reverberate to positively impact the world for millennia. Thank you for giving attention to this important topic. You have the power to make a difference between a manageable future and a painful one. I look forward to supporting you with complete and accurate science and to answering your questions.
Thank you very much, Dr. Wolkin.
Good morning, Chairwoman Johnson, Ranking Member Lucas, staff, and members of the Committee on Science, Space, and Technology. Thank you very much for the invitation to come speak to you today. As a citizen, I'm very pleased to be here, and I congratulate you on selecting this topic to consider. As a scientist, it means very much to me to be here to speak to you about evidence-based material, the data that we have to talk to you about today on glaciers and ice sheet change. I live in Alaska, and Alaskans are very in touch with their surroundings. The cryosphere is that place on Earth where water is in its solid form, so snow, ice, and permafrost. Recently, while doing some field work near Valdez, Alaska, it looks much like what you're seeing today. And so Valdez is in a fjord, used to be covered by ice. Now the ice is melting quickly. Upon completing a bathymetric survey, or mapping the lake surface below the water near Valdez Glacier, we were at the shoreline and reviewing our data. I'm very happy about what we've discovered, because now we can start to find out how much water in the lake is contributing to the melting of the glacier that terminates into it. A woman and her dog named Elvis, a slobbering basset hound, came up to us, and she says, "What are you doing?" And I said, "Well, we're trying to find out how deep the lake is." She said, "It's 600 feet deep." We looked at each other and said, "You're absolutely right. We just used $25,000 in equipment to figure that out. What did you do?" She and her friend went out in a canoe and lowered a rope. And they discovered that the rope wasn't long enough, so they paddled back to shore and grabbed the rope. And then they tied the extra rope onto it, lowered it down, and they discovered that it was 600 feet deep near the glacier. Now, she is a Valdez resident for 30 years. She said this glacier is melting faster than anything I've seen in the area. Where does all this water go? Well, the answer to that is in the oceans. And so Alaskans are keenly aware of their environment. They're keenly aware of the changes. This same woman lives in an area where outburst floods impact her house every single year. The glacier releases tremendous amounts of water, rips out the dike, challenges the bridge, and gives them an opportunity to see the power of change. So the cryosphere is changing in Alaska, and glaciers are a part of that. It's very important for us to understand what is happening. In Alaska, we have a very large state. It's 1/5 the size of the rest of the United States. It's huge. We have thousands and thousands of glaciers. We know changes physically on 3 of those glaciers. We have mass balance data that began back in 1966. And with those data, we are able to understand how glacier change is happening over long term. That is incredibly valuable to us. So most of the information that we have today is built on the shoulders of giants and the data that they were able to start collecting a long time ago. It's important that we start that process now. So collecting data now in various places in the state means that we can evaluate and quantify the amount of change that we have between now and whenever we're worried about the change. We do this so that we can build better computer simulations, so that we can plan. as policymakers and decision makers, it is imperative to have the right scientific information, and we cannot provide that without the money, without the funding, without the students, without the resources to be able to provide the information that is necessary for local stakeholders, such as the woman in Valdez and her dog, as well as important federally mandated decisions that have to be made in this country. So evidence-based decision-making is what we're after in order to have sound scientific change and be able to communicate to the local residents, such as those in Valdez and Alaska, so that we can actually start planning for some of these changes. Thank you.
Thank you very much, Dr. Pfeiffer.
Along with my colleagues, I'd like to thank you all, Chairwoman Johnson, Leading Member Lucas, all the members of the committee and staff. Like my colleagues, I was pleased, surprised, jumped at the opportunity to come and talk to you today about subjects that I've spent 2/3 of my life on. I've spent a long time living on glaciers and have had a good opportunity to see the changes and study them. As Chair Johnson mentioned, I'm a glaciologist. I've done this for 40 years, and I've had opportunities to work in landscapes that have changed dramatically over time, mostly in Alaska. I work mostly on the small glaciers of the world, the 200,000 glaciers other than the Greenland and the Antarctic ice sheets. And I wanted to talk mostly about them, and I really want to come back and focus on Alaska, which is one of the hot spots in the world, both literally and figuratively, in sea level rise, but also in fresh water flowing into the ocean, in fires and environmental change in the coastal regions. These small glaciers matter for a wide variety of reasons, and I also want to try to concentrate today on the reasons that have direct ties to the United States. There are a number of global issues. Water resources, water availability from the Himalayas, for example, is going to be critical for Nepal, India, Pakistan, Bhutan, places like that. They also produce significant geohazards of landslides, of flooding, what we call outburst flooding, as glaciers retreat and leave behind very unstable, steep slopes. When this happens in places like Nepal, these are very unstable landscapes in the same valleys where a lot of people live. It's one of the reasons that these hazards are as great as they are in the Himalayas. It's because we've got the mountains there, glaciers changing, and also people living in that landscape. That's one of the reasons that's not quite so much of a problem in the United States, is we're not obliged to live right next door to glaciers in most places, not all. They also have significant environmental impacts by changing the temperature of the waters the glaciers drain into and by changing the salinity of the water. One of the effects of Alaska that we don't understand particularly well yet, but we know it's there, is the fact that the ice sheet or the glacier runoff from Alaska that flows into the Gulf of Alaska in the Pacific works its way up through a gap in the Aleutian Islands and enters the Arctic Basin. And it turns out that that's quite a large chunk of the fresh water entering the Arctic Basin. And that fresh water influences, among other things, the extent of sea ice in the Arctic. We don't have a good handle on how much that flow is, in part because we're not making comprehensive measurements of the water flow into the Gulf of Alaska from glaciers. As my colleague, Dr. Wolken, mentioned, we're not monitoring the glaciers in Alaska very well. We're not really keeping track of them. So while we can see that they're melting, we can measure their height change, or we could up until recently anyway. We don't have good observations of where the water is going. We don't have good gauges measuring that flow. One of the last things that I want to come back to in my statement again, though, is sea level rise. As Dr. Alley pointed out, the ice sheets contain virtually all of the fresh water that's locked up on land in ice. You take all the other glaciers, about 200,000 glaciers, you only get about a foot of sea level rise out of them if you put them all into the ocean. But they're like a big bucket with a little tiny, they're like a small bucket with a big hole in it. That water is leaving the small reservoir very fast. And in fact, if you look at the combined most recent measurements of where new water coming into the ocean is coming from, more than 50% of it is coming from these small glaciers, and the remaining smaller percentage is coming from the ice sheets. Now, that's right now. That's in the short term. The longer term, the ice sheets are certainly going to take over. But in the short term, and this is a term, say, on the order of 30, 40, 50 years, where decision makers, planners, policymakers really need to have the most robust information, and they need the greatest handle on uncertainties. We have to look at the entire picture, the ice sheets and the glaciers and all of their consequences, of which sea level rise is just one. So I'll stop there for now and be happy to continue and answer your questions.
Thank you very much. That completes the testimony of our witnesses. We'll now begin our first round of questions, and I'll yield myself 5 minutes. While a lot of progress has been made in understanding current trends in glacier and ice sheet melt rates and predicting future changes, uncertainty still exists in the potential for tipping points, where the major parts of the Antarctic or Greenland sheets will collapse, and when and how much more sea levels will rise is yet still out there. So for all of the witnesses, as top experts in the field, what are the most pressing needs in glacier research in order to address these uncertainties? And the second question, given the differing impacts of glacier and ice sheet melts on global sea level rise, ocean temperature and salinity, nutrient cycling and ocean currents, fisheries, and even geopolitical tensions from diminishing drinking water supplies, how can multidisciplinary research approaches help address some of the outstanding questions? And we can start and just go down the panel.
Okay, thank you. You raise huge and important issues. You will hear several things as we go along here which are important. I'd like to highlight the people, the students who can really solve these problems have an amazing number of calls on them. They can go to business, they can go to finance, they can do all sorts of things. They have skills that are hugely in demand. We hope that a lot of them go to business and go to finance and do useful things out there, but we would love to have a few of the best students come to us. If those students look at our world and say there isn't funding, there isn't reliable idea that you can make a career in telling the public what's going on, they all will go elsewhere. And we don't want all of them, but we would really like a few of them. And that means funding for studentships, and it means some level of telling the student, if you commit to 4 years as an undergrad and maybe 7 years as a graduate student and a bit of postdoc to become a world expert on this, we will support you in doing that. And it is people, and we need a few of them to help us do this.
Thank you.
Well, I think there are three things, as I said before. One is fostering more research, and it's research across the agencies, because the U.S. has really been leading in understanding how the ice sheets are changing, and it's becoming increasingly important that that research, whether it's supported by NSF, NOAA, USGS, NASA, DOE runs a lot of ice sheet models. We have to recognize this incredible resource we have to be at the cutting edge of who's going to know and be able to provide the answers to communities around the globe. I echo Richard's workforce question. We really do need to broaden the number of people working on this, and not just glaciologists. We need engineers. We need computer scientists. We need to recognize that this is a significant national security and a national economic issue that requires all hands on deck. And then the third one is really to foster what NSF is now calling convergent science, science where you really bring together people from different disciplines focused on a problem so that we can address the problem. That NSF just released they're navigating the new Arctic, where that was really the focus of how do we go in, back to Ranking Members Lucas's question, how do we have science that brings together the people who are going to look at those problems? And NSF is really trying to foster that. The word currently is convergent, where you actually bring to people from different disciplines who are looking to solve a problem. And that's what we absolutely must do, both within the US and globally. This is a problem we cannot solve by ourselves.
Thank you. Dr. Moon.
Yeah, I'd like to emphasize first better understanding the glaciers and ice sheets themselves, the physical processes that we don't yet know. We've never been able to watch ice sheets collapse, so we can't look back into the record, and that requires going there, observing the systems, and doing process studies, and then integrating that information with computer simulations. The second thing is that these any projects within this need to be coordinated with other countries. Sea level rise, ice sheet, glacier melt are international issues, and we need international teams working on them. And anything you can do to help facilitate international collaboration, I think, is excellent. And finally, in your question regarding connecting different disciplines, this is a very difficult thing to do. Disciplines have been separated for decades. It's the way many elements of our academic system and our research system are built, and it requires long-term investment and an understanding that we have to create those relationships, because we're taking our information about glaciers and ice sheets and we're recognizing that they're part of a connected Earth system that includes people as well as plants, animals, and other physical components.
Thank you.
I will echo the comments of my colleagues in that we do need people. It's critical that we have people on these issues. I'll share with you just an example from one of my other projects, looking at snow distribution on glaciers and alpine areas. We've gone through 3 people now in a critical data science position because they can make more money elsewhere. And so it's really hard to retain the people once we have them, and it's really challenging to actually recruit these people. The other issue is, again, I'll emphasize Alaska is 1/5 the size of the rest of the United States. We have a lot of area, and we are data poor. We have only a handful of long-term observations in the state, and we have very few long-term records. And when I mean long-term, I mean beyond 12 years. So it's very challenging to work in that environment. And so what we really need is more observational information to go off of. And you know, we can do a tremendously better job with the science if we have data. The only way to make the models do better is to actually have data that drive the model. And so we don't have that right now. So we're doing the best we can. And one of the most important observation technologies that we had, Operation Icebridge in the state that monitors the height of glaciers, is now gone. It's been discontinued as a program. And so we can't do that anymore. And so the other thing I'll say is that I'll echo the comments of having a mixed bag of individuals to do critical tasks. And it's important for us to have a diversity of individuals working on these really important issues.
Thank you very much, Dr. Pfeiffer.
Well, after writing down my list of responses to your question, I realized that all I really have to say is I'm with them. We seem to be pretty much on the same page here, and I promise you we didn't rehearse this in advance. It really boils down to people and support to train those people. We've got these critical questions, the research questions. One of them is the tipping points. What's actually going on in glaciers and ice sheets that causes this occasionally very anomalous behavior? We can't model that problem out of the way with computers or with our knowledge of mathematics and mechanics. We actually have to get in, literally, in and under the glaciers to see what's happening. Decades ago, when I was, we don't have to run away and leave the building, do we? Okay. Decades ago, when I was a graduate student, and Richard will remember this too, we had programs all through the United States with opportunities for graduate students to work on small glaciers in Alaska, in the Pacific Northwest, in the Scandinavian Arctic, as well as in Greenland and Antarctica, where we could go back a number of times while we were students, really learn what is happening on glaciers. I'd already made 12 trips to Alaska before I finished my PhD. That's really not happening anymore. Most departments, and we've got an abundance of programs. We've got a lot of expertise out there searching for students, trying to bring them in, but we don't have the support to really go places to train them. And so we are producing a lot of computer modelers, very good, and they're doing very important work, but they're waiting for this knowledge to come in for them to put into these models. And we're really falling behind on that. Also, as Dr. Wolken mentioned, we're missing what's happening in Alaska. Operation Icebridge, which was our best way of tracking the loss of glaciers in Alaska, that's vanished for the time being. And monitoring of fresh water flowing into the ocean. We don't know what that is. So we need the answers to those questions, but to get the answers, we need people.
Thank you very much. I'm way over Mr. Lucas.
Thank you, Madam Chairman. Dr. Moon, let me turn to you first, and let's discuss for a moment. The federal government spends a lot of money on research. We have a lot of research dollars coming out of the National Science Foundation, the various department agencies, DOD. I mean, we're doing a lot of things. Let's talk for a moment about, from your experiences, what kind of suggestions you have about, in a more direct way, how do we make sure that the various federal research activities are better coordinated, integrated, as you noted?
Well, I can speak to one example that I think is a nice example for how to work on this. This is a program called IARPIC, the Interagency Research Program in the Arctic, and that program brings together people who are funded and doing work supported by different agencies. They have regular webinars, they have regular meetings, and it helps people communicate on what's going on. I think having those sorts of tools and having communication between agencies at the program manager level also encourages us on the research scientist level to be able to get information that tells us about what different agencies are interested in, so that we have a sense of the interest, the potential funding, and how they might be connected together.
Thank you. Dr. Bell, as I mentioned in my opening statement, I have a deep interest in weather patterns. I represent the northwest half of the great state of Oklahoma. I'm a product of my experiences, but I'm also impacted by the experiences of the people who came before me in my district. And where we are on the east side of the Rockies and the Southern Plains, my area was one of those that suffered dramatically in the Dust Bowl of the 1930s, the Great Depression. But in addition to that horrendous drought, which had a lot of government policy and farming practices that enhanced the misery, we went through a drought in the 1890s, drought in the 1930s, drought in the 1950s, the horrendous drought at the beginning of this decade. So you understand, as a farmer in the real world, where I come from when I ask my questions, how much does the scientific community understand about what will happen in the lower latitudes, weather pattern-wise, by what's going on in the glaciers? You see where I'm coming from here? Because glacial water changes the chemistry of the oceans, changes the temperature, that affects... I did pay some attention in my science portfolio at Oklahoma State.
Right, and one of the very clear predictions from the climate models is we're going to see a lot more of those extremes. We're both going to see a lot more droughts, and we're likely to see a lot more, what many of your neighbors saw, a lot more floods this year, because we all know we're here in Washington in the summer and it is hot and muggy. That is because hot air holds more moisture, and in the long run, that's going to make more floods. So, in terms of the direct linkage between the warming climate and the weather, that's the easiest one to think about. We are going to expect more extremes in precipitation, and we're going to expect more extremes in weather. The direct link between the changing land ice and changing climate is something we're still working on, is what we heard it from Tad, PFR is what will that water go into the ocean due to the ocean circulation? There's certainly hypotheses out there that the changing sea ice have contributed to some of the extreme weather we're seeing now. You know, that certainly that's on the table. But again, it's showing how we have not decoded the weather system and the climate system on our planet, but we can see the impacts already. You wanna-
Please, Dr. Alley.
Yeah, Representative Lucas, I'm sorry to interrupt. As you know, the great state of Oklahoma is fantastic in educating meteorologists, and you probably also know that there really is scholarship that shows that the federal investment in meteorology pays handsome dividends for the well-being of farmers, for the well-being of fisherpersons and others, and at a level that is a huge payoff on investment, and I can give you chapter and verse if you need it. There is great optimism now in the community that does weather forecasting that we will be able to move into that area which give more warning to the farmers of Oklahoma, the fisherpersons of Oregon and Maine as to what's coming. We can't guarantee that, but the optimism is real, it's palpable, and it's exciting.
And I just want to follow up with one thought following on Richard's, is that we have invested a lot in weather forecasting. That's why we now, I'm not a farmer, I'm a sailor, so I think about hurricanes more than droughts, sorry. But
You have water spouts, we have tornadoes.
yeah,
yes.
yeah, I do, and I worry about them too. They give me goosebumps. But we've been able to narrow our understanding of where those hurricanes are. I can plan much better when I hear there's a hurricane coming than I used to. And that's because we've invested in weather research, everything from the process-based work to the numeric, and that's what we don't have for the ice sheets yet.
Indulge me, Chairman. Dr. Volkin, what are you telling the state of Alaska about how to handle the circumstances in the next decade or so?
Well, Ian, that's a good question. I mean, we have some of the best climate modelers in the world at the University of Alaska Fairbanks, and they are doing a tremendous job in producing downscaled climate models for Alaska. Their products are only as good as the data that they can use to train those, and they've done a tremendous job in predicting out to, say, 2100 what the climate's going to be like. From that, we can make some estimates of how glaciers are going to respond, how the cryosphere in general is going to respond. And, you know, the tools, the best tools that we can produce are available, but we need to improve those tools tremendously in order to make better predictions so people can plan.
Thank you, Doctor. Thank you, Chairman.
Thank you very much. Ms. Bonamici.
Thank you, Chairwoman Johnson and Ranking Member Lucas, but really thank you to our witness experts who are here today. We do appreciate your expertise. I'm fortunate because I'm from the Pacific Northwest, where we still have glaciers in the Cascade Range and the beautiful Wallowa Mountains in eastern Oregon. And over the years, the snow and ice masses have really helped delicately balance our temperature, our water temperature, and our ecosystems. The nutrient content. Glacial meltwater has provided drinking water, and the runoff helps power our communities. Tourism and outdoor recreation are really important in our state. People travel to see our streams, rivers, and lakes, which the glacial sediment makes this iconic teal color. It's a beautiful place. You should all come and visit. But today, the glaciers that have once filled a lot of the hanging valleys and the moraines and the mountaintops across some of the most pristine regions are rapidly melting, and in large part because of anthropogenic emissions. On Mount Hood, which we can see from Portland, in my home state, the Sandy Glacier caves were once the largest glacier cave system in the lower 48 states, but now the glacier is melting at an alarming rate. And further north of Oregon at the Columbia River Basin, at Glacier National Park, they're losing the geologic features that provided its namesake. In fact, when it was founded in 1910, the park had about 150 glaciers, and according to a study from Portland State University and the USGS, the Park is on track to lose its remaining 26 glaciers in the next few decades. Dr. Moon, thank you for your testimony. You mentioned the role of glaciers in sustaining ecosystems, and in Northwest Oregon, the expedited rate of melting of glaciers could have significant consequences for our salmon and steelhead populations and threaten recreational and commercial fishing, tribes, species that benefit from healthy salmon runs. And as the glaciers melt and the water flows change and the water temperatures warm in the Columbia Basin, the tributaries and tributaries, the fisheries are threatened. So how quickly are these larger ecosystem changes taking place, and are there potential adaptation and mitigation strategies that we in Congress can support to help at this point in time?
I would say, and you might find too that you have many problems also related to those that are being seen in Alaska, and receive comments there. Certainly, we are losing those glaciers very rapidly. Just as you cited, we're seeing retreat and ice loss at rates that have never been seen in these areas. And so those fundamental changes that are happening rapidly and quickly are changing the ecosystem just as quickly. One thing to consider is that in many of these places, we initially see a bump in the amount of water because we're getting warmer air temperatures. We still have the glaciers there at the moment. So you actually get a bump in water availability. And we see communities also in other places in the world where they depend even more strongly on glaciers for drinking or irrigation water, adjusting to an added level of water input, which then, of course, is eventually going to decline substantially to levels below what it was previously. So they are rapid changes, and I think that there are many places where the research is not keeping up with the speed of these changes. That's true for us understanding the glaciers and the ice sheets themselves, and also certainly true for understanding the ecosystems that depend on it. So I think it may be a case where we are changing things that we are not even able to keep up with or see the true level of those changes.
Thank you. I appreciate that very much, and it's a good place for the Science Committee to get some more research funded. Dr. Pfeiffer, some of your colleagues at the University of Colorado Boulder published a study in 2017 about the effects of dissolved black carbon on glacial melting. The sooty black material that's emitted from gas and diesel engines, coal-fired power plants, and wildfires is a significant portion of particulate matter and contributes to climate change, as we know. The study found that the black carbon from the combustion of biomass and fossil fuels can enhance glacial melting, and as black carbon deposits on snow and ice surfaces, then the particles decrease the Earth's ability to reflect rays from the sun. So then that results in absorption of heat and faster melting. But it's also worth noting from the testimony here today that even if anthropogenic emissions were halted immediately, we'd still see the reciprocal effects on glaciers. So Dr. Pfeiffer, what are the most apparent gaps in the current modeling of glacier recession for various emission scenarios? And assuming that the U.S. achieved a net zero carbon emission policy by mid-century, where should we invest more federal resources in responding to the consequences of glacier melting?
So the process that you bring up, this black carbon, is it's hard to see when you're actually out there. It's quite a subtle effect, but very small particulate matter, which is carried into the air. And this was particularly a problem prior to the collapse of the Soviet Union, because there was a lot of coal burning industry in Siberia. It's far enough north for their emissions to get trapped in this atmospheric gyre in the Arctic. That's reduced a little bit, but not by a large degree, and emissions from further south still get into the Arctic basin and also elsewhere. Not all of Greenland is in the Arctic basin, for example. Southern Greenland is exposed to air masses that come off of Europe and North America. So there's a lot of mixing, and this material continues to be deposited. I think that the understanding the surface energy balance, things like if you make the surface of an ice sheet just a tiny bit darker, how much effect will that have? That understanding is pretty well in hand, but we need observations. And simply knowing that it happens isn't enough. I really do think, though, that the basic needs go beyond that to simply making the observations. There are so many parts of the world that were, until recently, really in the dark. A lot of high mountain Asia, so the Himalayas and other ranges, that's been partially addressed by remote sensing, but again, not all of it. Some of this work just has to be done on the ground.
Thank you. And I see I'm out of time, but Chairwoman Johnson, I request unanimous consent to enter into the record the study from the University of Colorado.
Without objection.
I yield back. Thank you.
Thank you. Mr. Brooks.
Thank you, Madam Chairman. Is anyone on the panel not familiar with the Earth's last glacial maximum roughly 20,000 years ago? Okay, everybody is? Good. For those in the audience who are not, by way of background, during the last glacial maximum, Northern Europe was under ice. Roughly 90% of Canada and almost all the continental United States of America, north of Missouri and the Ohio rivers and east of New York City, under ice. According to the United States Geological Survey, during the last glacial maximum, again 20,000 years ago, sea levels were roughly 410 feet lower than today. Stated differently, for 20,000 years, sea levels have risen, on average, 2 feet per century, versus the much less, roughly 1 foot per century rising rate since 1993 that is reflected in Dr. Alley's written testimony. Finally, per Zurich University of Applied Science, Earth's average temperature 20,000 years ago was 48 degrees Fahrenheit versus 59 degrees Fahrenheit today. That's an 11-degree increase in global temperature average over the last 20,000 year period. So my question to each of you is, and we'll start over here with Dr. Pfeffer and move from my right to left, did human beings cause the global warming that started 20,000 years ago and continues through today? Or if not, what did?
So the examples from 20,000 years ago that Mr. Brooks gave us they're excellent examples of the kind of natural variability that the Earth experiences. And there's no question that in the past there have been changes in temperature, in sea level rise, in weather patterns, and climate generally, as dramatic or more dramatic than what we may be experiencing in the future. And of course, they weren't human-caused 20,000 years ago, or in the last million years. All of these variable events have been occurring throughout the Earth's modern history.
Well, my first question was, in your judgment, did human beings cause the global warming that began 20,000 years ago during the last glacial maximum?
No, absolutely not. It's an example of spontaneous natural variability, one of the many ways that this whole system, whether you look at it in terms of sea level rise or temperature or storms, can be varied.
Are you familiar with the phrase snowball Earth or slush ball Earth, roughly 600 million years ago when we were almost entirely ice or slush?
Entirely natural variation.
Versus the Paleocene and Eocene thermal maximum of about 55 to 56 million years ago when the average temperature was roughly 73 degrees Fahrenheit, which is 14 degrees warmer than what we're experiencing now. If you don't mind, Dr. Walken, let's go to you. Did human beings cause the global warming that began 20,000 years ago?
No, absolutely not. That was just a product of natural variability in the climate system. Yeah.
Dr. Moon?
Humans weren't around in nearly the numbers we are today, so we certainly weren't available to be combusting fossil fuels at the rate we are today or putting emissions into the atmosphere. You can consider we've built America in the last 243 years, and we're changing things at a much more rapid rate.
So you also agree then that the global warming that has occurred over the last 20,000 years, that 11-degree Fahrenheit increase in temperature was not human-caused, at least when it began 20,000 years ago?
So I would agree that when it began 20,000 years ago, and we're coming out of the last glacial, that was not caused by humans. The warming of the last 100 years most certainly was.
Out of curiosity, why do you, or how do you explain that the sea level rise average over the last 20,000 years has been 2 feet per century, yet we're down to 1 foot per century?
So much of our rise in sea levels that you're talking about came earlier in that 20,000 years.
first 6,000 to 7,000 years.
Over this last 10,000 years, we've been sitting with very stable sea levels, and those stable sea levels have allowed us to develop the coast of the
All right,
world.
thank you, Dr. Moon. And I only have about 30 seconds left for Dr. Bell. Dr. Bell, in your judgment, 20,000 years ago, global warming, when it began, was that caused by humans?
In my judgment, the variation that we were seeing 20,000 years ago was part of the pulse of the planet. It pulses at 100,000 years, glacial, interglacial. When I started graduate school, we were expecting to go into the next glacial period, except that we as human beings in the last 100 years, and you can see the kick up, since we invented the steam engine, you can see the temperature moving up.
All right, I'm out of time, Madam Chairman. I appreciate your indulgence. I just wish I had sufficient time to actually get into what the cause of the global warming that began 20,000 years ago was, if not humans. Thank you.
Excuse me, go ahead, Doctor.
I just wanted to respond a bit further to your question. The changes in the past there are two significant differences between those events and the events today. One of them is that they were triggered by natural variations, not by human agency. And let me just give you an analogy of your house. Your house might burn down, and it might burn down for entirely natural reasons, might be struck by lightning. But it could also burn down if you're careless and you drop a cigarette in a crack on the sofa. Both of those are triggers that result in your house burning down. The presence of one of them doesn't really say much about the other, except that they both lead to the same endpoint. The other thing is that while there were these very dramatic temperature changes and sea level rises in the past, which were entirely natural, we weren't there to deal with them. The problem here is with people. How do we respond to environmental change? The Earth will take care of itself. It doesn't really care what happens. It's what people do. And if this had happened a long time ago when the population of the Earth was a few 100 million, it probably wouldn't have mattered either because we could have just gotten out of the way. But as it is today, with the numbers of people that we have and the infrastructure, we're very sensitive to changes of this kind. We don't handle change very well. For example, suppose that the conditions for growing crops that exist today in California picked up and moved to North Dakota for a couple of 100 years. There were variations like that in the fairly recent geologic past that occurred. How would we deal with that? It's an entirely different world than what we're not here to experience, but we know about 20,000 years ago. We're much more sensitive. We don't deal well with change, and to deal with it, we need to know a lot about it.
Dr. Pfeffer, thank you for your additional insight.
Thank you very much. Mr. McNerney.
Well, I thank the chair for calling this hearing, and I thank the witnesses. I appreciate all your testimony this morning. Well, the planet is continuing to warm up, and I believe we are going to blow past the 2-degree centigrade marker that people say is the limit of tolerability. We need to be looking at all the potential tools in the climate solutions toolbox, especially if we're to take action to prevent the collapse of the West Antarctic and Greenland ice sheets. That's why I introduced the Geoengineering Research Evaluation Act last Congress. It didn't pass, but just introducing that caused the National Academies of Science to explore the state of research and climate intervention strategies, as well as the need to implement a governance structure of those technologies. Dr. Bell, given the complexity of the climate system and the risks associated with further human interference, how do you think the U.S. should approach the field of research on climate intervention?
Both the National Academy and AGU, the American Geophysical Union, have statements that say this is an issue that we must research. If done wrong, it could be terrifying. But again, it is the same problem that we have been saying before. We don't have the sufficient workforce looking at the issue, evaluating it, and building the body of knowledge to evaluate whether or not it is a good idea. To me, I come back to the very, very few examples of geoengineering of the ice sheets that are out there. And to give you the idea of how many groups have done it, I think 2 groups have put it on the table. You know, one is basically you get a bunch of snow blowers and put more snow back on the ice sheet. Problem is, it turns out if you put snow blowers on the ice sheet, it gets steeper and it flows back in the ocean. Didn't work. The other idea is to build, bigger than the Panama Canal many times, walls to keep the ice sheets from being attacked by the warming ocean. These are ideas being put on the table by a small cadre of glaciologists. What this illustrates is that we need, as a species, to research this, and we need not just glaciologists, not just atmosphere scientists, but we need to bring the full suite of talent to the table to think about this, because as we address climate change, we're going to probably need to look at every tool that we have available. That's what we found when we did the building down the street.
Thank you.
We couldn't do one thing.
Dr. Alley, do the risks of abrupt change in the Arctic and Antarctic indicate that we should be serious about technological interventions such as sunlight reflection to maintain stability?
So I would echo what the National Academy and what the American Geophysical Union have said, which is that we need the knowledge base that will allow you, all of you in this learned body, to actually make wise decisions. We don't yet have that knowledge base. There are real issues with international governance, as you raised, and thank you. There are real issues with reception by people. I can tell you stories of geoengineering, cloud seeding, that led ultimately to a professor from Penn State having a hole shot in his car door because the local farmers were very unhappy with the idea of cloud seeding. Sort of how this plays out into the broader populace is sometimes not as obvious and as simple as you might imagine. So I think gaining this knowledge base so that you would then have the capability of making wise decisions is wise.
Thank you. Again, Dr. Alley, the West Antarctic ice sheet has been noted to have the greatest amount of uncertainty in the melting and breaking rates. How much of the uncertainty related to West Antarctic ice sheet can be addressed by additional research, and how much is dependent on the future rates of warming?
Right. Certainly the uncertainty can be reduced by the research, but it is already very clear that if the faster and the more we warm, the more likely a failure will be. So in our world, mitigation, trying to slow down the warming, buys you time. It buys you time to learn. There is always some danger with the tipping point that you pass it before you see it, and it's too late to slam on the brakes. It's too late to turn and avoid the iceberg, and very rapid warming, that becomes more likely for West Antarctica as we run into the future.
Well, what are some of the, Dr. Bell, perhaps, what are some of the major concerns about the collapse of the West Antarctic ice sheet?
The major concerns are that it could go fast, and we don't actually know how fast. It's back to the ice sheet. There used to be an ice sheet in New York and in many of the states here. We didn't see that one collapse, or the residents then who didn't record what was happening. So we as a species don't have the record of how an ice sheet collapses. So we worry about what happens to the ocean, how the ocean chews at the bottom of it as the ocean warms. We worried about what happens when the surface melts. Where does that water go? Does it fall into cracks and act like a jackhammer to open it up? Or does it run off like a river? There are some major fundamental understandings about how warming air, warming ocean impacts ice. And in that sentence alone, you see how we have to have different disciplines talking to each other.
So Dr. Moon is working on this problem in Greenland, and Dr. Pfeffer is working on this problem in Alaska, as is Dr. Wolken. So the truth is, what we learn spreads broadly.
Well, I hope the other three panelists don't feel neglected, but I only have 5 minutes, so I'll yield back. Thank you.
Thank you very much. Mr. Babbitt. Changing of the guard.
All right, musical chair, sorry about that. Dr. Wolken. In addition to serving here on the Science Committee, I also serve on Transportation and Infrastructure, and I represent Southeast Texas and have 4 ports in my district. I recognize the importance of our navigational ship channels. With that being said, one of the things I find very interesting on this topic that's relevant to my committees and my district is the possibility of 2 trans-Arctic commercial shipping routes that are opening up. This isn't to say that I want to see all the glaciers melt and the sea levels rise uncontrollably, but if there are inevitable changes, I want to make sure that the United States is positioned to be economically fortified, and I know that the Russians are certainly exploiting newly opened up shipping lanes, ice-free zones, and even claiming that certain areas that were considered international waters are no longer that, but belongs to Russia. So if you see the Department of Transportation, how do you see the Department of Transportation or even the U.S. Coast Guard interacting with coordinated multi-agency collaboration that you say is needed?
Yes, thanks for the question. I'll answer in 2 ways. The first is that what you speak of is really an incredibly important issue, and economics and national security really do come to mind, and that's a sea ice issue in the north principally. And reduced sea ice, of course, is offering opportunities to enter into the Arctic and explore and ship. And that comes with fantastic opportunities, of course, and a lot of perilous conditions that could cause lots of environmental damage if not done right. Having a multi-agency approach is incredibly important a little bit farther south, and you mentioned the Coast Guard. We have changes in Alaska that are impacting many of the fjords and the transportation routes in the south. And some of the changes in the cryosphere, changes in the snow, the ice, and the permafrost in the mountains are unpredictable to us right now. We don't have enough information. And so the Coast Guard communicating with various universities and agencies about how stable the slopes are, about how fast conditions are changing in certain areas could really be an asset to the Coast Guard as they respond to emergencies or possible disasters from cruise ships or fishing boats in different areas. I will point out an example of in 2015, there was one of the world's largest snow rock avalanches into the Tyndall Fjord. And in the process of that collapse, the tsunami that resulted from the rock falling into the fjord was enormous. It caused a trim line, like the bathtub ring, that was around 600 feet high, and any fishing boat caught in that, or Coast Guard vessel, or tourist ship, would have been destroyed.
Right.
So communication about the data that we have to the individuals who will be working in these different areas, the federal agencies such as the Coast Guard, it's critical that we have this conversation.
Absolutely. Thank you very much. And one other question. Some experts have predicted that our currently available mapping and navigation and ship capabilities are going to limit just how frequently and successfully we use these potential routes. And Dr. Wolken, and to all of our witnesses, when conducting research on ice depth and volume, is there also efforts to improve commercial shipping potential, such as data needed for mapping? Dr. Wolken, I'll ask you first, and I'll go to Dr. Pfeffer.
Yes, a lot of the work that's being done in the fjords in Alaska are specifically focusing on the nearshore environment. And so the exchange of dynamics of interactions between the glaciers and the water and that environment. And so in the process of doing that, wonderful maps of the fjord are being generated. Lots of different surveys of the coastlines are being generated in the process. And so the really great part about this is that we can have overlapping interests being served with good research in the right areas. And I think that's where this idea of having these interagency collaborations, these multiple perspectives, this team approach is really important.
Okay, great. Dr. Pfeffer, I think you wanted to.
Yeah, I wanted to respond because your description of the situation in Texas reminds me a little bit of an experience that I had about 5 or 6 years ago, where I was employed as a consultant for the Prince William Sound Citizens Advisory Committee, which is an environmental group that was set up in the state of Alaska following the Valdez oil spill to provide environmental oversight in Prince William Sound, which includes the town of Valdez and southern terminus of the Alaska pipeline. And their specific concern was icebergs. The Columbia Glacier in Alaska, which is one of the glaciers that I've worked on for many years, was a major iceberg producer, and those icebergs came out into the shipping lanes. And the Alyeska, which is the operating company for the pipeline, and the Coast Guard were both concerned about what future iceberg hazards were going to look like. Specifically, they had an ice detection radar system that had come to the end of its useful lifetime, and they had to replace it. And what their specific question was, do we have to be worrying about icebergs for the next 100 years or the next 5 years? And so I worked with them for, it was about a 2-year period, developing some simple models based on how much of the glacier was left and our best prediction of what the retreat would look like, to give them some sense of what the iceberg discharge would look like. It was a good opportunity to collaborate with a state-level agency and also with the Coast Guard. We have a limited amount of bathymetry for that region. It would be good to have more, and NOAA has done some surveying in there. But that kind of interagency cooperation could be a lot more frequent than it is. And when it does happen, it's extremely beneficial. It certainly was a great help to us in Alaska.
All right, thank you very much. Appreciate it.
I have a quick addition to that, in that just last summer, we saw one of the first groundings. I actually saw the vessel before it grounded, of a Russian icebreaker that ended up grounding in the Northwest Passage. Exactly the places we're hoping, or we're thinking may be opportunities for more connections across the high Arctic. So it is a critical issue because it ran aground on uncharted rock, in essence. And the other piece is that the Coast Guard provides critical infrastructure to support the work we do in Antarctica. Without the U.S. Coast Guard and the heavy icebreakers, the U.S. could not run the flagship programs they do. And we are seeing the Asian countries invest deeply in icebreakers. The Chinese government has invested in 2. The Koreans have a beautiful new icebreaker. We need strong icebreaking capability, both for ability to engage in the Arctic and continue to be leaders in Antarctica.
And we have a shortage of icebreakers, do we not?
That's why I thought this was a moment to remind you of that. 'Cause
okay.
it really
Thank
is. Both boats run aground, and we need icebreakers.
All right, thank you very much. My time is long expired. Thank you.
Thank you very much. Mr. Caston.
Thank you, Madam Chair. Thank you all so much for being here. Earlier this Congress had an Environment Subcommittee hearing on the impacts of climate change on our oceans and coasts. Our experts were talking about what we need to do to stay below 1.5 degrees of warming, and I asked them, if we got rid of all CO2 emissions tomorrow, how much sea level rise is already baked in? And the answer was an unequivocal 2 feet. I think that's consistent with your testimony, Dr. Alley. That is frightening, but I have in some ways I have a bigger fear that's the deficiencies of our little Homo sapien brain. And I want to demonstrate this, and I want all of you out in the audience, you get to participate now. We're going to do a little experiment. So this is real easy. I'm going to say 2 things, you give me the next in order. A, B. A little louder, come on, you got this. This isn't hard, thank you. All right. Second one, 2, 4. You're all wrong, I was looking for 8. This is the problem, right? We have all of these nonlinear trends, and our little brain says 2, 4, 6, and we see all these things that are going on. And Dr. Alley, I think you alluded to this in your testimony. And so, if 2 feet is baked in, and if the likely skew of that data is not a bell curve, but on the more frightening end of the spectrum, what sea level rise should we be planning for within the zone of possibility?
I surely wish I knew. This is a frustration for us at a level that is deep, and I wake up at 2 in the morning and I look at the ceiling and I say, what do I tell somebody? I can remember coming back from Old Ironsides on the water taxi while doing the Freedom Trail in Boston and sitting in the water taxi and putting West Antarctica into Boston Harbor and not knowing what to do, which is, I mean, I'm sorry, it is very self-serving for me to sit here and tell you that funding research is good, because it might go to me or my students.
So I'm
but
not- so
we
I'm not-
want to know.
So I'm not asking you for certainty, and I appreciate, look, I started my career I got a master's of science in chemical engineering. I get the caution, but we got to sit on this side of the dais and make decisions. So I'm just asking, if you were in our seats with uncertainty of information, what is the range that we should be thinking about in our zone of possibility?
Yeah, don't go below the IPCC and start thinking about flexibility. Think about adaptive capability.
I'm just asking for like a number of feet.
Yeah, I can't give you a number.
How about how about a timing? How soon? How long do we have before 2 feet is locked in?
Yeah, very soon, if not in. So for the 2 feet, you're getting close. But the big numbers, it really is, I mean, a good business person looks for the black swan, but they don't know when a whole flock of black swans is coming. And so they really do look to their best people to be ready, which is
let
your,
me-
that's you.
I want to get to a couple other things on my time, but the reason I asked this question is in part because the same day that we had that hearing, I sit on financial services, we had Federal Reserve Chairman Powell in, and I said to him, I just had this hearing, you are responsible for helping us write 30-year mortgages. Do you factor in whether or not those mortgages are going to be paid off in low-lying coastal areas? And the answer was that he thought we probably should start thinking about that, but we haven't yet. We have a whole host of issues here that go just beyond whether the sea level is a little higher, right? We got housing. I live in Illinois where we've got, polar vortex and polar bombs or whatever the term is of this year, because as that ice melts, we're destabilizing global weather flows and shifting that cold air down temporarily until we all get a lot hotter. Dr. Wolken, I had a little fun doing a little Googling on the weather report on Moose Mountain where you live. I understand you got a huge, unseasonable amount of rain a few hours ago. I understand that is pretty positive because you've got some concerns up there. Can you just help explain to me what's happening on Moose Mountain that makes that rain good and how that is related to the fall off in sea ice?
Wow, that's a really good question. I will preface this with some history about the winter. It was a very low snow year. We didn't have near the snow that we would normally have, and this is a trend, especially across the Arctic. And this year, it's been unseasonably hot. In fact, this week in Alaska, many records have been broken, and this is common as well in recent years. I left Alaska the other day to evacuation notices. So before I came here, we were planning to evacuate our house because fires were raging just near our house. And so the rain coming is a great idea. The whole state is suffering from smoke right now because there are so many fires, really resulting from a chronic low snow issue and having warmer temperatures that are really fueling the fires. And so this is a major issue for us, and it's become quite personal for me.
So just last question for the whole panel. Has anybody estimated how many people's homes are at risk because of this combination of sea level rise, spreading wildfires, flooding in the Northwest? How many people do we need to be thinking about dealing with right now? Do we have any estimate of that answer, Dr. Moon?
So I'm going to give you an estimate that's just a fraction of those things that you just asked about. This is just an estimate on homes. It doesn't include power plants, airports, military bases, anything else, just homes. If we're looking at 1 foot by 2035, that would be about 140,000 homes. If we're looking at 4 feet of sea level rise, that's about 1.2 million homes. If we're looking at 2 feet, that's about 300,000 homes. So it's in the hundreds of thousands, and if we look at levels where we're reaching 6.5 feet of sea level rise by 2100, we're looking into the $1 trillion kind of mark just for homes. That's not other roads, other infrastructure, et cetera.
And I would presume that's just coastal. That doesn't include Dr. Wilkins' house that may be at risk.
And it
because
doesn't
of
include wildfires or any of those other things that you mentioned that will be also addressed by addressing climate change.
Thank you. I yield back.
Thank you very much, Mr. Beard.
Thank you, Madam Chair and Ranking Member. I guess my question deals across the board. We got all doctors here as witnesses, so the question I have simply, what federal programs are most critical to gaining a greater certainty on the future change in ice sheets and those effects on sea levels? So you can go in any order you want. Dr. Alley, you want to start?
Right, it is interagency. National Science Foundation provides so many of the people support, and they do the lead agency in the Antarctic and in some other things. NOAA, we have to have what they are doing. NASA has been a keynote on, not only on Icebridge, which we have been talking about, but the satellite monitoring. The DOE has a role in modeling, and so it is, I've hit a lot of the high ones, but it really is the interagency. The U.S. Geological Survey, when I gave the number on how rapidly the icebergs were breaking off when John Muir was watching, that number came from the United States Geological Survey. So, so it is having these wonderful centers of excellence that you have built that live in the U.S. government and give us leadership. They are not localized in one place. They are in several agencies, and they work together. They know each other, and they can do this with support.
Thank you. I'll remind you that Madam Chair only gave me 5 minutes, so we spread that out.
Well, I will echo the NSF for understanding why, NASA for monitoring how it's changing, the USGS for incredibly important measurements of the glaciers, DIE for modeling, and NOAA for lots of information about how the ocean's changing and what the fundamental tide gauges are doing.
Thank you.
You asked about narrowing our range of what's going to happen into the future. On the science side, integrating better observations and understanding of the physical system into our models. Our models can't make up that information on their own, but I also want to reiterate that it is our emissions pathway that is going to make a tremendous difference in what that future number of sea level rise and our future number for ice loss is. That's not the science part.
Yeah, I just want to echo the comments of my colleagues here and really just add that we're doing this in Alaska already. We're getting as many people together as often as possible to try to solve some of these issues. The only way to really do this is through an interagency perspective, and there's really no other way to address such a large issue, and all of the federal government programs are critical to what we do.
Okay, well, again, I'm echoing what all of my colleagues have said, but I want to add to this the problem of collaboration and communication between these agencies. It's not an easy task. One example, NSF operates on a principle that can be summarized as turn the brightest people loose on the most interesting questions. The fundamental function of NSF is to support these individual investigator-based science where each one is evaluated on its own scientific merits. It's not a mission-driven agency in the way that, say, NASA is. That has produced, it's been extraordinarily successful by letting scientists decide on what's the best thing for them to study. But in a situation like sea level rise, I think that let's put climate change generally, not just sea level rise. I think that a more coordinated approach is necessary. Back in the early 1970s, National Science Foundation had a brief program called RAND. This is Research Applied to National Needs, where basically a management structure was experimentally imposed on research programs. And it was a notable failure. Almost everybody that you talk to that knows about RAN would say, oh boy, yeah, that was a bad time at NSF, but not everybody. It's a little bit like the Manhattan Project. If the Manhattan Project had started out with the advisors saying, okay, we need to understand about atomic energy. All of you pick an interesting problem, go work on it, and come back in 5 years. That's not the way the Manhattan Project worked. And I don't think we're going to solve this problem that way either. I'm not talking about the magnitude of the project or how much money should go into it, but I am talking about coordination and the need for some really innovative thinking about how those agencies should interact. Because it's hard. It's hard to steer scientists, and it really is a herding cats problem. But particularly with all these agencies, there needs to be some really imaginative way of figuring out what gets done first and how long do we have to solve it. And I don't have any answers to that, but I think that's a really strong need.
Thank you, and I'm out of time, and I yield back.
Thank you very much, Ms. Wexton.
Thank you, Madam Chairwoman, for yielding, and I thank the witnesses for appearing today. It has been quite alarming, to say the least, to read your testimonies and also listen to the responses to some of my colleagues' questions here today. It's absolutely clear to me, and it should be clear to everyone, that we are at a tipping point of our Earth changing dramatically and irreversibly due to human-caused climate change. It's even more alarming that we're locked into 2 feet of sea level rise. Everybody seems to agree about that. And that given the melting of the Greenland and Arctic ice sheets, we could be looking at 11 feet of sea level rise. And how you prepare for that is something that is really important to all of us, and certainly to me and my home state of Virginia. We have a lot to contend with over that. We are home to Naval Station Norfolk, which is the largest naval base in the world, and Langley Air Force Base. They are already having to deal with the effects of sea level rise and the effects it has on our national security. And I'm also the mom of 2 kids, and I worry about what kind of a planet we're leaving for them and their kids. I know that we had some questions about climate, ice cover, and sea levels and how they routinely change from season to season and over time. Some claim that this natural variability means we shouldn't be concerned with humans changing the climate. Dr. Alley, I know that Mr. Brooks asked a little bit about this, and Dr. Pfeffer did give some explanation of what is actually happening. But Dr. Alley, can you explain what the science tells us and why we should be concerned with the changes in ice and sea level and climate that we're seeing right now? What makes it different from what happened, over the past 20,000 years?
Yes. So thank you very much. It's wonderful that people take interest in what we do. So, as you know, on a dry, hot summer day, the hills of Virginia have always burned when there was a lightning storm. And because you know that, if you see kids headed out on a dry day with illegal fireworks, you are very worried about it. We know that people have always died, so we have metal detectors at the front of your building here. We know that climate has always changed, and that proves that climate is changeable. And you've never met the person who said, the hills have always burned, so we won't worry about arson. But you have met the person who said the climate has always changed, so we won't worry about humans changing the climate. The climate has always changed proves that the climate is changeable. The climate change has always affected living things, which proves it's important. Climate has changed for a lot of reasons, but CO2 has been especially important. And that points a finger at ours. Now, if you were an arson investigator, you better know natural fires. You do CSI fire. If you're a homicide investigator, you do CSI homicide. We do CSI ice. We do CSI climate. And we actually have very high confidence that what is going on now is human, not natural. If anything, over the last small number of decades, nature has tried to cool it off a little. So how much of the warming has been us is a little bit more than all of it, is the central estimate. But the fact that nature has done these huge things in the past. That when nature warmed a little bit, sea level rose a lot. And then you say, well, we could cause a whole ice age of warming with our CO2 in the future. And the last end of an ice age gave us 400 feet of sea level. There's 200 more left. So I believe that climate has always changed is a very, very strong argument to be concerned about what we're doing for climate in the same way that burnable hills make you nervous about arson. And when
related to that, Dr. Alley, in your testimony, you discussed several studies that suggest that the IPCC report is overly conservative and underestimates the rate at which ice sheets are and will continue to melt.
I have great difficulty finding any evidence that they are overly alarmist, and there certainly are things that point to the possibility that they have been low in the past. And yeah, that's fairly clear. When you look at the history of...
Can you discuss this current scientific research on estimates for tipping points for the Greenland ice sheet, Arctic ice, and Antarctic ice? What are the tipping points, or what does the science tell us?
So Greenland, if it gets, as it gets thinner, it gets warmer. As it gets warmer, it melts faster and gets thinner, and at some point it will be committed to loss. It probably will melt fairly slowly. West Antarctica, if it starts doing what the glaciers in Alaska have done, the coastal glaciers have done, it could go very, very rapidly. We're cautiously optimistic that the sea ice in the Arctic will act like a dial rather than a switch, but we're not entirely sure of that. We are worried a little bit about circulation in the Atlantic and other places that act more like a switch or a tipping point. The National Academy of Sciences looked at tipping points in 2013. They especially pointed to tipping points in ecosystems and in human systems. So at what point, when people are stressed and they're having to move their houses or change what they do, at what point do the people become very mad and then tip into some other level of behavior? And so when you look, there are some physical tipping points, there are more ecological tipping points, and there may be a whole lot of people tipping points.
Thank you very much. I see my time has expired. I yield back.
Thank you. I'll now recognize Mr. Gonzalez for 5 minutes.
Thank you, Madam Chair, and thank you everybody for being here for this important hearing. I want to focus, at least the beginning of my time, on adaptation and resiliency. I think, unfortunately, it seems like there's a lot that's sort of locked in that we're going to be dealing with over the next however many years. And I'll start with Dr. Pfeffer. What are you seeing, or what guidance can you give us with respect to making sure that we can adapt as sea levels rise, and that we're building more resilient infrastructure?
As I mentioned in my early comments, I really am concerned with, in the work that I've done in the near term, the next 30, 40, 50 years, where this whole constellation of factors has to be considered. One of the very interesting and extended conversations that I had is with a man named David Bihar, who works for the San Francisco, the city of San Francisco as a coastal engineer. And one of the problems that they have to deal with it's a very large dike system, basically surrounds San Francisco Bay. And they need to know how far do they have to raise this dike system, which is extremely expensive. It's in the billions of dollars for a very small rise. And so it was not adequate to simply say, well, let's just be safe and figure on 10 feet of sea level rise. And then you only get 1 foot and you've spent an awful lot of money.
Yeah.
In the same sense, one of the questions, and this goes back to an earlier question about how many people may be displaced by sea level rise. If you take an overly conservative number, meaning let's take a worst case scenario, and you draw a line on the coast saying, okay, this is going to be inundated by such and such a date. What happens to the value of those homes on the basis of that line that you've drawn? And the nearer in time you get, the more important that becomes. So you really have to have a tight bound on sea level rise and a tighter bound to the nearer to the present that you get. We don't really have that yet. In some places we do, and it very often is a group of scientists that live in a particular region, like Hudson River, for example.
Yep.
Well, San Francisco Bay is another example, where you can look at all of the causes of sea level rise, including things like isostatic depression or rebound in an area, as partly as a result of large-scale things like ice sheets disappearing 20,000 years ago, and partly local things like putting buildings on that land.
Yeah.
There are a lot of different factors that have to be considered, and different timescales. You deal with different factors, and I think it's another thing that points to this interagency collaboration.
Got it.
But one of the things that I've tried to emphasize in the past is there's certainly a cost to neglecting sea level rise, but there's also a cost to overestimate it.
Yeah, and I think that's actually a really important point is, when we talk about resiliency and adaptation, there is a cost to all of this, right? And
Yeah.
we can't completely ignore that. We can't be too conservative or too aggressive, or we're going to be wasting a lot of money. Dr. Wolken, if I could shift to you quickly. In your testimony, you mentioned that in Alaska there are only 3 long-term continuous records of glacier mass for the entire state. Considering remote sensing and computer modeling are used to predict future scenarios due to the lack of ground-based observational data, how reliable and accurate are remote sensors and computer modeling in measuring glacial melt and predicting future changes?
Yeah, we're doing really well with these different tools, and I think one of the things that you can envision is if you go to the hardware store and you get a laser rangefinder, for instance, from the shelf, and you do some home renovations at your house. Well, that laser is actually quite accurate. It's a laser, and it's very precise and accurate, and we use tools like that to really gauge how the ice is responding. We use other remote sensing tools to do similar things, to see how much it's changing in this direction. And those are incredibly useful, and that's how we do things. We do those with both airborne and satellite-based assets. There is a need in places like Alaska, where the topography is so extreme and where the changes are so great, to actually have ground observations. And so when you're using these different remote sensing tools, the resolution isn't quite there some of the times. And so having ground observations to validate in some way or to correct in other ways is really the way to go. And so more ground observations truly do help us. With a lack of that, we have no option but to use the tools that are in front of us, and really remote sensing based opportunities are where it's at for us.
Great, thank you, and I yield back.
Thank you. I'll now recognize Dr. Foster for 5 minutes.
Thank you, Madam Chair, and I'd like to thank really the ranking member and all members of this committee and the witnesses about the tremendous increase in the level of serious discussion that we're having on issues like this over the last 2 years. I think if you Google my name along with Greenland, you're led to a video of a previous witness who was a lawyer trying to convince this committee that it was a matter of scientific debate whether or not it was a good thing that the Greenland ice sheet melted. Okay, and so we're having a long overdue and very high quality discussion here. Now, my next question is, how many of you knew Charlie Bentley? Wow.
He was my PhD advisor.
Well, I grew up next door to Charlie Bentley on Lake Mendota in Madison. And, it strikes me, and I remember sitting on his porch discussing what he did. He would disappear every couple of years and study the ice sheet in Antarctica, which just seemed goofy. And I think it's a lesson on curiosity-driven research, that this thing, over the course of his career, went from something that was done by a, sort of an eccentric professor to something that is now going to be an absolutely crucial thing in deciding how we deploy trillions of dollars of capital to try to mitigate the damage of this. And so Charlie passed away, I think, a couple of years ago, and I understand there is a mountain named for him in Antarctica. Anyway, that's neat. I was pleased to see the recognition among the committee here. Now, my next question I had is, what is known about the speed of response of the ice sheet system to changes in temperature? You know, there are natural experiments when you get volcanoes going off with a couple degrees swing for a few years, and is that long enough to actually be seen in the response of the ice sheet? And the reason I'm asking this question is, I think it's likely that we'll be able to decarbonize the U.S. economy. I think it is much less likely, since we're 5% of the world population, that we're going to be able to convince the rest of the world to decarbonize as quickly as necessary. And if that happens, then I think it's likely we'll be looking at things like albedo modification, and which has the potential of very rapidly changing the temperature. There's an article in Nature earlier this year that used state-of-the-art climate models to say, okay, you know, will it work, or are we going to get cyclones and so on? And the first look was that it might be feasible. But they didn't, to my remembrance, model anything having to do with the ice sheet. And so I was worried that maybe there was sea level rise locked in just due to the thermal time constants, that even if you rapidly bring down the temperature of the atmosphere, that it will take a while. And so what is known in modeling or in data about that issue?
The ice sheets respond, they're slow. I mean, when Richard and I started studying ice, we couldn't imagine they'd change as fast as I mean, Charlie, actually, one of my first papers I wrote told me I couldn't write that they were going to change fast, because even in the 1980s, we couldn't imagine the speed at which we're seeing now. And now you can actually occasionally hear fear in scientists' voice because they are changing faster than Charlie thought they could when you grew up next to him. That we just couldn't imagine these thick pieces of ice changing, and he couldn't either. But now we know they're changing to the ocean warming and the atmosphere. The atmosphere is a faster driver than the ocean. So we don't have a good handle on how fast it's going to.
Do you have models that even make a decent approximation? Can you see, for example, in response to volcanic eruptions and the swing there, can you see changes in the rate of ice accumulation or deaccumulation?
We can do a lot of it right and a lot of it not yet. And so I could brag on the progress that we've made, and some of it with Charlie's help, and I could bore you or scare you with where we're missing, especially the couplings into the ocean. So if you start blocking the sun, what it does to the atmosphere is fairly straightforward. What that does to the ocean, which is interacting with the ice, is not at all straightforward, and that really needs work. And there is.
Are these computing limited problems or knowledge limited problems?
Yes, especially knowledge limited. The computing is coming. We could use a little more, but it's primarily knowledge limited.
Yes.
It also has to do with those measurements, that our lack of knowledge of even what the ocean temperature is around Antarctica. We can measure the top of the ocean, but we're still so limited in understanding what's going on at depth. And that's what matters, because the critical parts of the ice sheet that are really the sensitive switches, those are down low, and we don't have the good measurements.
Mm-hmm. Let's see. Now, I'll abuse another 20 seconds. No. Yeah, for the last.
Yeah, I wanted to add, it's already been mentioned that the IPCC's fifth assessment, their discussion of sea level rise is very conservative. I was one of the lead authors in Chapter 13, which is the sea level chapter, and that discussion that we had about what number are we going to put in for our upper limit. I remember that very vividly. And essentially what we did is we said we just do not know yet enough about the rapid tipping point mechanics to be able